All right. So give me just a second to share my screen. All right, so hopefully people can see this, yes? You can see my screen now? Awesome. So last time we had talked a bit about, got all this stuff. We talked about one-to-one. And remember that one-to-one is this idea that different inputs go to different outputs, right? So it's never possible to have two inputs going to the same output. Another way to say that is if I'm looking at, let's see, you can probably see this. Let's make it blue. Here, I'll make it green so we can sort of see it. If we're looking at something like AX is equal to B, right? There's only one solution, or at most one solution. Right? Because a solution corresponds to inputs, right? A solution corresponds to inputs. So if there's at most one solution, then there's at most one input that goes to that given output, right? B here is my output, okay? So we had talked about this. And one of the things that we had talked about was in order to have at most one solution, we can't have any parameters. So that means that we cannot have any free variables, which means that every variable has to be a leading variable. We're talking about a pivot in each column, right? And so I just remind you, right, in order for this to work, we need a pivot in every column in order to be one-to-one. Okay, and I'm going to erase that because I'll need it next time. Okay, so we have another matrix here, this matrix A, and we are thinking about whether this gives a one-to-one linear transformation as well. And so the first question it says is, how many vectors are sent, excuse me, how many vectors are sent to 0 by t? Another way to say it, again, here, 0 is my output, and the solutions to this would be my inputs that go to 0, right? So when I solve that, I'll go back to blue again. So when I solve that, I'm looking at this matrix, A times X is equal to 0, right? And so if I wanted to solve it, I would augment my matrix. So I would look at this matrix here. And, you know, in order to solve this, I would do reduced row echelon form, right? If I were to reduce row echelon form that, I'm going to guess I get this, turns out. Right, that right there. So tell me, for this particular matrix, for this particular linear transformation, how many solutions are there, and how do you know? I don't need to write down all the solutions. I just need to know how many solutions are there. Can somebody help me out with that?
Infinitely many.
Why infinitely many, Chase?
Because you have the form 0 equals 0.
Right.
And
So the 0 is equal to 0 just tells me that it's consistent, right? That's the only thing that it is. But I agree. I think that last row is helpful. There's one other thing that I think is important. Chase, what do you think?
yeah, it also has a free variable.
Right.
So that means that we have a parameter.
Good. So it's this column that's missing a pivot, right? So this is a free variable, which means infinitely many solutions, right? It's that free variable right there, column. That's what it is, right? Here, because it's a 2 by 2 matrix, that last row of zeros sort of indicates that it has to have a free variable. Good. So this has infinitely many solutions. Is T one-to-one here? What do we think? I agree. Is that Laura that's shaking her head? Laura, tell me why.
We had just said that there had to be a pivot position in every column, and in this case, it wouldn't satisfy that.
Good. So it's missing a pivot in a column, right? I mean, the other way to think about it is, right, one-to-one says that you cannot have two inputs mapping to the same output. Here, there are infinitely many inputs mapping to the same output 0. Infinitely many inputs map to output 0. Right? So infinitely many inputs are mapping to that same output 0. Okay? Good. So any questions about this one so far? Yeah, again, the key thing here is that it's missing a pivot in a column. Okay. And I should say it's missing a pivot in a column of just A, not the augmented matrix. So we should note that. In a column of A, right? It's really, really easy to get confused between the pivots in the augmented matrix and the regular matrix. So I wanna pay special attention to that. Here's a theorem that's interesting, and it just says that generally, if we want to check 1-to-1, we really only need to check whether AX is equal to 0 has only the trivial solution. We do not have time as a class to prove it, so we're going to move right on to ON2. So any questions about 1-to-1 before we move on to ON2? All right. So let's see about ON2. So ON2 says, the definition says, T is onto if for every vector W in Rn, there exists at least one vector U in Rm, such that T of U is equal to W, right? So again, I'm thinking of this guy right here as an output, right? Or a possible output. It's a possible output. And I'm thinking of this thing right here as an input or a solution, right? This is the input, which I should also be thinking it's a solution to an equation, right? That thing on the inside, the U is a solution, if there is one, if there is such a U. Okay, so I have given you a very boring matrix, and I'm asking whether this is onto. So I'm going to think about the equation AX is equal to B. I know that this equation may have 0, 1, or infinitely many solutions depending upon the matrix A and the vector B. If the equation has 0 solutions for some B, then would that mean that T is onto or not onto? Explain. So, and I'm going to scroll back up to make sure we have that definition there. If there is 0 solutions, what would that mean?
So if all the solutions equal 0, or they're just no solutions?
If there is one output for which there are no solutions, just all we're looking for is one output where there's no solutions.
Would that even be a linear?
That's a good question. It still could be a linear transformation. But the question is, is that particular output hit or not, right? That's sort of the question, right? So if I have a particular output, if I'm thinking about this as a possible output, right? And I have that possible output where there's no solution to it, right? That would mean that there is not at least one vector that maps to it, right? So this means not onto. No inputs map to this particular let's do to this output B. Okay. Right. So again, I'm thinking of B as my output, and I'm asking any solution would be something that maps to B. So if it has 0 solutions, that means that nothing maps to B. It's not onto. Stuff is missed. Okay. Right. So 0 solutions means that it is not onto. Okay. The next question says, how can you tell from the echelon form of A whether the equation has 0 solutions for some B? Okay. What am I looking for here in order to discern whether there are 0 solutions or not, whether the system is inconsistent or not? What am I looking for here?
Like a 0 in the last row.
Good.
Set equal to something.
Exactly. So in augmented, yeah, that's exactly right, Carrie. Thank you. So in augmented, let's see, in reduced row echelon form of augmented matrix would need a row like this. 0, 0, 0, 0, 0, something non-zero, C, where C is not equal to 0. Right? That's what I'm looking for. Right? That's the only way to have something have 0 solutions, be inconsistent. So when I think about this, again, this is an augmented matrix. Where would the pivots, sorry, I'll just move on. Sorry, I'll get this on the next one. So I'll say maybe that is missing a pivot in row left of line, left of that vertical line, right? So if it's missing a pivot in a row, that would mean that you've got this whole row of zeros, and then to the right of the line, you get something that's non-zero, right? So it's missing a pivot there, okay? The next part says that we want to connect this to other stuff that we've done. So let's think about that. This is actually an idea that we studied in a different context, the idea of whether there is a solution to AX is equal to B for all vectors B. So does anybody remember? I'll just ask that. And if not, I can help us out. Yeah, it's totally okay. This is exactly the question of our Roomba and whether our Roomba can get to all points. Okay, so if there's always a solution, that means that there's always a path for my Roomba, right? So I will say this is like the Roomba question. Can Roomba get to all points in, well, now I don't remember what it is. Let's make sure I get it right. Okay, sorry. In Rn, or do columns of A span Rn, right? So the question of on2 is the same question as do the columns of A span Rn? Same question, exactly the same, right? Chase, you got a question?
Is it columns or rows?
Always columns, great question. Always columns. We will talk a little bit about rows, but no, it's almost always columns are the things that we're interested in. It's a great question. It's a great question. Yeah, and sort of the reason is because if I think about this notation, this A times U, that is a linear combination of the columns of A. Okay, so that's sort of what we're looking at, right? Is there a linear combination of these columns of A, right? And so it really has to do with columns. Good question. Oh, that's not what I meant to do. Let's try again. There we go. Okay, so, and I think that we're ready to do this. Fill in the blank with either the word row or the word column. The linear transformation T is onto if and only if the echelon form of the matrix for T has a pivot position in every, what do we think?
Column.
Not column. Try again, McCary.
Row.
Totally right. Carrie nailed it the second time. Nice job, Carrie. I appreciate you being courageous and putting that out there. So why is it row? So remember, exactly as Carrie said, right? This part right here tells us why it's a row, right? Because in order to tell whether it's consistent or inconsistent, I need a leading one in those rows, right? So that's really the question, right? And so I'm going to go by and put row. I'm going to say something like, explain my answer. If there is a pivot in a row, then reduced row echelon form. Whoa, that's too many R's. Let's try again. Of augmented matrix cannot have a row like this. Right? And if it cannot have a row like that, then we know it has to have a solution. Does that make sense, right? Because again, if it has a pivot in that row, then I'm not going to get that all those zeros. I'm going to get 0, 0, 0, 0, 0, 1, right? And as soon as I get that 1, then I know I can solve it, right? Any questions? So do we feel okay with this? All right, so if we go back up here to our matrix A, this one right here, is this one going to be onto? Is this matrix here going to be onto, and why? Chase says yes. Why Chase?
Because it has a pivot in every row.
Good. So T is onto, pivot in every row. All right, pivot in every row, which is what I need. All right, so I'm going to move over there. I think that's it. Oh yeah, so that's what I just did. So I can do that here too. T is, it says, whoops, we're going to say, is it onto? T is onto, pivot in each row. Right. So this idea of onto really is all about looking at the rows, like 0, 0, 0, 0, 0, something else, right? It's all about looking at those rows. So that's the reason why onto is connected to this idea of a pivot in every row. Whereas one-to-one is all about, are there infinitely many solutions? Right? Are there infinitely many solutions? In order to understand whether there's infinitely many solutions, I need to look at the columns. Okay, the columns will tell me if there's infinitely many solutions. If there's a column that's missing a pivot, that tells me that there's a free variable, and that tells me that there are infinitely many solutions. Okay, so that's why the idea of one-to-one is connected to a pivot in every column. And I'll just very briefly say, I believe very much in giving you lots of practice for things that are, like tests that are coming up. Number 10 is really just some practice. Okay, so it's these sorts of questions are the types of questions that I would ask on a test, and I don't want you to go into that test blind. I want you to sort of have some experience working on some of those yourself, right? So I'm going to scroll back up to the top. Are there any questions about this material before we talk about the test?
Just really quick on the onto part for A, would that mean that it would be onto and one-to-one?
Turns out, yep.
Okay.
And that's a great question. So Laura, this time our matrix is square. It has the same number of rows as columns, right? So if I knew that it was one-to-one, that means that I knew that it had a pivot in every column. Since it's square and the number of rows and columns are the same, I know it must also have a pivot in every row, right? So in fact, for a square matrix, they're the same idea, strangely, or they're very closely connected. And in fact, if you check the new version of the unifying theorem, it's going to say exactly that, right? For a square matrix, that linear transformation being onto is equivalent, is the same idea as the linear transformation being whatever the other one is. I forget what I just said, right? But again, those two things are exactly connected. Again, that's only for square matrices. You could imagine a situation of a matrix where you had a pivot in every row, but not in every column. right? Or you could imagine a differently sized matrix where it's vice versa, right? So again, for square matrices, it's exactly the same. It's a great question. Other questions?
I don't know about everybody else, but I could not find these lecture notes on Moodle or the ones from the last set before
Oh, that's a great question. Did anybody else, was anybody else able to find them? They're not there? And nobody told me?
I think it was in maybe the announcements, but it was never put into the folder.
Oh, I apologize.
Yeah, it was on the email for last time.
I promise that I also put it here. It just didn't, I don't know why it felt like it didn't do it. But they are there. They are there now. I apologize, Carrie. I wish you'd let me know because I could have easily uploaded that a long time ago, and I apologize. But again, they're there now. So thank you for that. So any other questions about this? All right. So the last thing that I want to do, I want to just very briefly talk about the test. I think I'm going to stop my screen sharing too, maybe so I can see your faces a little bit more easily. Let's see. There we go. Your test, again, is on Thursday. So it's going to be a very similar sort of thing where it will show up on Moodle at 8 o'clock. So you'll have access to it. Of course, it would be against the honor code to share with the other section or with other students what is or is not covered on that test. And the first thing I'll ask you to do is to pledge your name to signify adherence to the honor code. So remember, if you have not yet passed your computation quiz, you won't get a calculator on that test. And the way that I'll be monitoring that is that if you have not passed it, then I will make sure that I will only, sorry, it's too many words in my brain. It's 8 o'clock in the morning. If you have not passed the quiz, I'll require that you show your work. Okay. And if I don't see the work posted there, then you won't receive credit for those questions. Now, of course, if you have access to a calculator, if you've passed that quiz in time, then sorry, I'm gonna check one more thing. Okay. I'm gonna go back. If you have if you're allowed to use your calculator and you just put on your test like reduced or echelon form equals, right? Because that'd be fine. I would expect that you have used your calculator for that, and that is totally okay. That still counts as showing your work. You know, I would definitely write down the reduced or echelon form just so I can sort of see what you're doing. So yeah, but again, if you haven't passed that computation quiz, I will be looking for your work, displayed out. Okay. And at the end of that class, I'll ask you to do the same thing, take a picture of it and upload it to Moodle. So any questions about the format of the test or anything like that? Okay, awesome. So I was going to say, I know that I see at least one message here that that there's some Wi-Fi. There can be some Wi-Fi issues for some students. So I just remind you that I'm recording this. We'll record the other section as well. My Wi-Fi is okay, so I think the recording should be okay. So if there's anything that you miss, rest assured that you'll be able to watch this video later on. And this time I will not forget to post it. I usually do a good job posting the videos. All right, does that make sense? All right. So I'm going to open it up now. So if you have questions that you want me to work, either from challenge problems from lecture notes we didn't get to, WebAssign questions, test review, test one that I posted, any of those things would be great if you just tell me what you want, and then I'll share my screen and we'll take a look at it together.
Is everyone finished the quiz and turned it in? Because if so, could I ask a question about the quiz?
Everyone has, I think everyone has. So let me double check before you say that, Hannah. Yeah, sure. You can absolutely ask a question about the quiz.
Can we go over the last question?
Sure.
I think I did it right, but I want to make sure I know what I'm doing.
Sure. Let's see. I'm going to pull it up. Oh, totally. So, so I'm gonna share my screen here. So give me just a second. I'll share my screen and I'll do what I will do what I did. I will show you what I got. I'm gonna share it. Come on. I forget how to make a new note. This shouldn't be that hard, should it? Nope. 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 That's not what I wanted. Hold on. Awesome. All right. So you guys should see a blank screen now. Yes? Okay. So I am looking at this matrix 1, 2, 3, 4, 5, 6, and I want to multiply it by this vector 0, -1, 1. So in order to multiply a matrix by a vector, remember it is the linear combination of the columns of A with these as weights, right? So these things right here are weights, and these are the, oops. So it is a linear combination of these three vectors, 1, 4, 2, 5, and 3, 6, with weights 0, -1, and +1, right? So honestly, if you gave me this answer right here, I'd be happy, right? You could also compute that, right? So you could compute that if you wanted to. This first thing is 0, 0. This next thing is -2, -5, and the last thing is 3, 6. So if I add all those things together, let's see, the first entry is 1, and the next entry is 1, I think. Does that look right? Did I do that arithmetic right? So again, the vector gives the weights of the linear combination of the columns of A. Does that make sense? Any questions about that? And does that make sense?
Yes, sir.
Awesome. All right, that's a great question. What other questions can I answer for you today?
Maybe we can wait until the end, like if other people have questions, but I would maybe like to go through the challenge problems of the linear independence notes.
Okay. Why not? I mean, I'm going to say we'll start now. So let's at least look at a couple of them, and maybe that'll help. And then maybe I could take some other ones. Carrie, does that sound good? So you said linear independence, right? Challenge. Oh yeah, these are hard questions. Totally. Trying to think the best way to do this. Yeah, that's hard. Yeah. So, I mean, Carrie, was there one that you wanted to start with?
I guess I just want to check that 11 was n less than n.
Okay. So I'm gonna write that up. So you guys can still see my screen. So it says when can when can m vectors span Rn? Right, justify your answer. So yeah, it's hard because m and n is hard for me to wrap my brain around. So what I always think of is I just sort of make up a particular value for m and n. Okay, so maybe let's say m is equal to 2 and n is equal to 3, just as an idea first, and then we'll sort of think about it. So what if m was equal to 2 and n was equal to 3? That means that I have like let's see, this would be 2 vectors in R3. Would it be possible for 2 vectors to span R3? What do we think?
Yes, I keep getting it confused with linear independence, like the spanning.
Yeah, those, and that's hard, right? It's definitely a hard question. So I guess the question is, if I put these vectors in a matrix, do I need a pivot in every row or column? Is the big question, right? What do we think?
Row?
I think so too. Okay, if I have two vectors in R3, right? So that looks like two columns. So my matrix looks like this. Right, my matrix looks like this. Would it be possible to have a pivot in each row here? How many possible pivots could I have?
Only 2.
Right, because I've only got two columns. So there can only be there's a pivot in each column, right? So, so this would be a maximum of 2 pivots, but would need 3 pivots. So no, not possible here. Not possible here. Right. So in this case, M was less than N. So if M is less than N, it doesn't look like it's possible at all. So I might say something like, if M is less than N, cannot span. So maybe my answer should be need M to be greater than or equal to N in order for vectors to have a chance to span. Right? Does that make sense, Carrie? Go ahead.
Yeah. For the next one, it says, under what conditions of M and N can M vectors in Rn be linearly independent?
Mhm.
To say vectors are in Rn, doesn't that mean it's spanning Rn? Or
No, that's a good question. So to me, to say that they are in Rn, it means that each vector has n components.
Oh, okay. So they have the same number of rows.
Right, and in fact, did they have? I mean, the number of rows is n here, right? They're in rows. Yep, totally.
And for linear independent, that's you need a pivot in each column, right?
Mm-hmm. Mm-hmm.
So
Can you
then-
make a guess? I mean, so can you make a guess as to what number 12 is? Again, number 12 says same question, only when is it possible to be linearly independent? Right.
and greater than or equal to M.
I think so. It's going to be exactly the opposite, right? So for answer, n is greater than or equal to m. So I want to go back to maybe the last one too and think about that a little bit more. Remember, spanning tells me, can my Roomba get everywhere, right? Do I have enough different directions for my Roomba to get everywhere? If I think about it, would it be possible to have 2 vectors in R3, 2 different directions of travel in R3 and be able to get everywhere? Well, no, right? I mean, if I'm in R3, I really need at least 3 different directions of travel to be able to get everywhere, right? That's the only way that my Roomba, or my drone in this case, is going to get everywhere. So that should be another way to sort of think about this, right? On the other hand, let's say that I had 3 vectors in R2. I had 3 different directions, but I had a drone in R2. Would that be possible to get everywhere? Totally, right? 3 different directions, and all I really got to get is to my plane. That would totally be possible if they're the right vectors. Right? I'll just say, so n is greater than or equal to m. Let's see. Would need at least as many oops. Oh, now I'm mistaken. Anyway, Yeah, I need more, sorry, n is, yeah, sorry, I need more rows than columns. Right? If there were too many columns, if there were more columns than rows, then I could only have one pivot in each row, but then I would be missing some columns, and that would be bad, right? I would be missing some columns. Does that make sense, Carrie?
Mhm.
Cool.
When you were just saying how you can have 3 directions, but only spanning R2, is that what you were saying? Would that mean, like, phrased in an example, that would be like a vector with 3 rows, but you're just trying to figure out if it spans R2, not R3?
Well, if it has 3 rows, then that tells me that it's R3, right? So you know what I mean? The number of rows tells you sort of the dimension of the space that you're in. So what I'm thinking of is this. Let's say that I'm in R2 and I have 3 different vectors. My Roomba can go in this direction. Sorry, let's get
Oh, okay. You're talking about N.
Yes. Let's say that my Roomba can go in those 3 different directions. Well, if it can go in those 3 different directions, it can get everywhere, right? I mean, it really, the first 2 directions are enough. If it can go sort of left, right, and up, down, of course it can get everywhere.
Mm-hmm.
Yeah, it's weird. And I will say, the M and the N always confuse me, right? Which one is M and which one is N? But the way that I think about it is, how do I do this? The way that I think about it is I place vectors as columns. So a 2D vector will mean matrix has 2 rows, right? So if my vector is something like 2, 4, right? When it goes into my matrix, that's going to tell me it has 2 rows. Does that make sense?
Yeah.
It's hard for me to wrap my brain around M and N, right? It's almost impossible for me because they're so abstract. So I try to make it very concrete for me by thinking, well, what if I have a 2-dimensional vector? What if I have a 3-dimensional vector? What would that look like? And what does that tell me about my matrix? Those are good questions, Carrie. Do you have another question?
Yeah, I think I get 13 and 14,
Awesome.
but 13 says like show that 0, U1, U2, UM is linear dependent.
Mhm.
On the test, could you write like, oh, no pivot in column 1? Is that enough?
Totally be enough. Yep, that would show it. Totally.
And then 15, could we do that one or like an example of it?
We could. So let me, before we do, I want to make sure that other people have a chance to ask questions. So let me give someone else a chance, and then we'll come back to 15 and 16, Carrie. Does that sound good? Laura, did you have a question? I feel like you had a question.
Oh, I have many questions.
Could
we go over what exactly for associated homogeneous systems, like what question, if you said, give the general solution or give the specific solution, like what that would look like?
Yes. So I'm thinking the first question on the practice test. Have you taken a look at that?
Okay. Sort of.
Let me pull that up. Let's see. So stop sharing my screen. Let's see. Yeah. So I'm going to share this screen instead. Can you guys see my, you guys can see my screen? Yes, hopefully. It's got test 1 key. So if you notice, it says, consider the following linear system, solve this system. So the solution is written there, right? So I've circled the answer here. Sort of it extends over there to the right. Do you know what I mean? Does that make sense, Laura, so far? Well, it says, In part B and C, it says give a particular solution to this system and give the general solution to the associated homogeneous system. So every answer that you write down, every solution can be broken apart into 2 bits, a particular solution and then that general solution, okay? This first bit, the part without the S's, that's your particular solution, XP. And the second bit, the part with the S's, that's your general solution to the associated homogeneous system. So maybe your question is more about what is an associated homogeneous system or what's the point of all that?
Yeah, just because I know that, it equals 0 at one point and then it doesn't, but it's associated, yeah. So if you could.
So associated just means it's not this system, it's one that's closely related to it, right? So like a business associate, you might say. So the business associate would be if I took this whole system and I replaced the -3, -2, and 2 with 0, 0, 0. Okay. And basically all this means is if I were to plug this, you can't see my mouse, can you? Probably not. Oh, you can't see my mouse. So this part right here, the S1 3/2 1 0 0, this XH here, it's probably not XH. It should be XG. I get confused. XG for general. If I were to plug in 3/2 S1, 1 S1 0 0 in for X1, X2, X3, and X4, I would get 0, 0, and 0 over here. Do you want to see that? Yes? Okay, so let's see if I can do that. I'm going to have to stop sharing my screen and share my new screen. All right, can you guys see my screen? You guys cannot see my screen. Nope, not yet. Hold on. Now you can see my screen, yes? Hopefully. Okay, so let's see. If I do something like, I'm going to write down this thing plus 3x2 plus 5x3 minus 2x4. Remember for the, well, I just do that, right? My x general was equal to, let's see, I'm going to write it in a slightly different form. Right, I just multiplied that S1 through. Okay, that's what my XG is. I'm just going to plug in these values, right? That top value is X1, the next value is X2, etc. So if I plug in, let's give me a little bit more space, perhaps. If I plug in, I get -2 times -3/2 S1 plus 3 times plugging in this value plus 5 times 0 minus 2 times 0. So if I just plug in those values, what am I going to get? Oh, that doesn't look right. Why is that not right? I think I've made a mistake somewhere. I don't get 0, do I? That's not good. Let's be sure I wrote it down right. Oh, sorry. I plugged in the wrong thing. Sorry. I should have plugged in positive 3/2 S1 instead. So I'm going to erase that. So it's like it's not even there. I'm sorry. Now what do I get when I plug in?
0.
Now I get 0. I could do the same for the other 3 equations. I would get 0 and sorry, other 2 equations, 3 equations. I could do the same for the other 2 equations. I would get zeros there. That's what it means to be a solution to the associated homogeneous system. Does that make sense, Laura?
It does. That cleared a lot of things up.
Awesome. Are there other questions I can answer from anybody else? And I can go back to somebody else. Chase, yeah, go ahead.
Yeah. Can we go over a number 3, but with 3 vectors instead of 2?
Are you talking about on test 1?
Yeah.
Number 3. Number 3?
Yep.
I'm not sure I could make up one on the spot that would be interesting. For 3 vectors instead of 2?
Yeah.
Um,
I think there might be a WebAssign one I could try to find.
if you knew which one it was, I could show you that. Yeah, Chase, I'm gonna have trouble coming up with something that is a problem that would actually make sense. Do you know what I mean?
There's number 6 on section 2 homework. It has 3 vectors and 3 components in each.
Gotcha. Well, give me just a second, and I'll see if I can find it. Whoops. Laura, which homework was that?
2.2.
2.2. Sorry, like number 6, you said? Yeah, I could do that. Okay. So let's see. So first I'm going to show you what it looks like. Yeah, I don't have a, oh no, there it is. Okay, do you guys see the assignment previewer should have number 6 up here on WebAssign? Okay, I see yeses. Okay, good. So it says find all values of H such that the vectors A1, A2, and A3 span R3, where A1 is given, A2 is given, and A3 is given. So I want to find all values of H such that they span R3. So everybody at least get a sense of what my question is? Okay, so I'm gonna go back to the other screen, which means I have to hide this one, but I'll sort of write as much as I can there. Let's see. There's no fast way to do this, sadly. Oh well. Okay, so I'm going to write down the 3 vectors. The 3 vectors were 2, 4, and 5. H, 8, and 10. And 1, 2, and 6. Right? And I want to know span R3. So the first question I've got is, I mean, spanning R3, that's a hard abstract concept. Let's relate it to something that's easier for us to understand. What's the best link? What should I think about? What does it mean to span R3? What am I looking for here?
Rows.
I need a
Right.
pivot in every row. That's right. Need pivot in every row. Need pivot in each row. So what I'm going to do is I'm going to stick these vectors in a matrix and start doing row operations. I can't use my calculator because my calculator probably would be unhappy if I tried to plug in the variable h, so I have to do it by hand. Let's see. So I first sort of want to get zeros underneath that pivot there. That I'm going to choose 2 as my pivot, and I'm going to try to get zeros underneath. Oh, that's gross. That's okay. We'll do it anyway. So let's see. My first row is fine. Let's do -2 row 1 plus row 2 becomes my new row 2. Let's see. I get a 0 here. I get an 8 minus 2h here. And minus 0 here, I think. Yes? Does that look right? 2. Yeah, I think that's right. Okay, so the next one is awesome. It's -5/2 row 1 plus row 3 is my new row 3. Let's see here. So that's 10 minus 5/2 h. and whatever 6 minus 5 halves is. I don't feel like doing that. I'm just going to leave it like that. So 6 minus 5 halves. It's beautiful. Are we good so far? Yeah, so I'm looking at that second column here. I need a pivot in every, we said we need a pivot in every row. Yep. What should I do next? Looks pretty hideous to me. I
Get
might
a zero. Oh, sorry.
go ahead. Oh, say it again, Carrie.
Get a pivot in row 3
Okay, good. So why'd you choose row 3?
because we need a pivot in each row.
Got it. That makes sense. I will say, I think what I want to do is to get a pivot in the second row and use it to get a pivot in the third row. Do you know what I mean? So I really should be thinking about that. I'm going to try to get a pivot right here. Okay. How could I get a pivot right there? I'm going to do something like divide row 2 by 8 minus 2h. Okay. And when I do that, I get 2h1, 0, 1, 0, blah, 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 something. I guess that's it. That's the whole thing. Right. And then I definitely need to get rid of that, this thing right here I'd like to get rid of. That I gotta get a 0 there. So what I might do is, oh my goodness, multiply row 2 by 10 minus 5 halves h. And I'm gonna put a negative in front of it and add it to row 3. And that's gonna become my new row 3. Now that seems pretty gross. Oh no, that's not so bad. That's not so bad. Sorry, I thought it was a lot worse than it was. 2h1 0 1 0. Does anybody see what happens when I do that? I definitely get a 0 here. I get a 0 here. That last one in that lower right hand corner, that's actually pretty easy. Does anybody see why that's easy? Because I'm multiplying some horrible mess by 0. What happens when I multiply a horrible mess by 0? It's just 0, right? It does not change this thing right here, which is 6 minus 5 halves. All right, so I'm very close to being done here, I think. Does it look like it was possible to get a pivot in every row? Totally. Is there any value of h that would be bad, that would make this process be bad? And there is one. Whenever I divide, what do I need to make sure that I'm not dividing by? I can't divide by 0, right? I cannot divide by 0. So I'll just note, cannot divide by 0. So if 8 minus 2h is equal to 0, we have problems. And if I solve that, I get h is equal to 4. This would be bad. Right, so if h is equal to 4, then that whole process breaks down. Right, if h is equal to 4, that whole process breaks down. Does that make sense? So the answer is any h is going to be fine as long as h is not equal to 4. Right, the only bad h is equal to 4. So Chase, does that help? I never would have come up with a question that actually would work on the fly. So I'm glad that Laura had one in her holster. Yeah. All right, we got about 9 minutes left, so I want to be sure that everyone gets a chance to ask some questions. Who else got a question who hasn't asked one yet?
I have a question about number 6 on the practice test. We don't need to go through it. It says on the key that we went through it in class, and I was just wondering like what notes or where
Oh.
that is in our notes.
Yeah, we may not have, because that was a note to the last time I taught this. Number 6, you said?
Yes.
Oh yeah, totally. So it says we worked carefully through why the answer that you gave is true. If you look through your notes on span, I could probably pull them up. Let me pull them up. So Becca's asking about number 6 on the practice test. So let me look. Let's see. Yeah, so I can show you where that is. So hopefully you can see my screen. I am looking at our third lecture notes on vectors and span, okay? If I look at number 15 right here, 15 sort of takes me through that process.
Okay, thank you.
You're welcome. So I mean, what you do is, this time I had a vector A and B, and I think on the test, it might be A, B, and C. I forget what let's look. It's gonna get angry at me, but that's okay. Yeah, this is in R3. So in this question, instead of having an A and a B, I'd have an A and a B and a C, and I would augment my matrix with the A and the B and the C, and I'd start to do row operations. And then I would sort of look to see if I've got pivots in the right spots. So number 15, I think, is gonna help you sort of figure that one out. So that's a great question. Any other questions about that one? All right, does someone have a question who hasn't asked one yet? Who has not asked one yet? All right, Carrie, do you want to go back to your question?
Let me see if I figured it out. Oh, I guess 15 and 16, they asked for us to prove. And so 16, for example, I knew it says prove that if a set of vectors is linearly dependent, then adding additional vectors to the set will create a new set that is still linearly dependent.
Mhm.
And I knew that was true because you're adding a column.
That line of reasoning is perfect, right? That would be a perfect proof.
Or do you have to
That'd be good. No, you could. I mean, if it starts out to be linearly dependent, right? That means that you're already missing a pivot in one of the columns, right? And if you add a new column, that doesn't change the lack of that pivot in the previous column, right? So no,
Right.
your reasoning is exactly right on. It's exactly what I would be looking for.
Okay.
Yep.
And then 15 is prove that if u and v are linearly independent, then so are the vectors u plus v and u minus v.
Mhm.
Oh, would it be a matrix of u plus v and u minus v, or are we looking at them separately?
Yeah, I'm not sure you can do that using a matrix. I think you have to sort of, I don't think that's going to work. So let's say this. Let's say that they are linearly independent. Okay, they're linearly independent. So I'm going to see if I can pull up the screen again. Okay, so let's see. I mean, let's say U and V are linearly independent, right? Let's think about U plus V and U minus V, right? So I need to think about the definition of linear independence, right? So the definition of linear independence is, let's look at solutions 2. right? Linear independence has to do with solutions to an equation that looks like this, right? You know, values for x1 and x2 that give this, right? Let's say, let's see here. Yeah. Yeah, I'll say that. Let's say there are non-trivial solutions to this. Okay, so let's say that, you know, like for instance, for example, x1 is equal to 2, x2 is equal to 3, just for an example, okay? Just for an example. Something like 2 times u plus v plus 3 times u minus v is equal to 0, right? Because that's what it would mean. Sorry, that's the opposite of linear independence. That would mean it's linearly dependent. Does that make sense? It's linearly dependent. Okay. If there's non-trivial solutions. Look, I'm going to rewrite this. I can rewrite that this way. Let's see here. This is the same thing as 5u. Does that make sense, Carrie? I just sort of put my u stuff together and my v stuff together.
Mhm.
Yeah. But look, this is a non-trivial solution to x1 u1 plus x2 oh, sorry. Let's try again. So what I'm saying is if I get a non-trivial solution to the one involving u plus v and the u minus v, then that gives me a non-trivial solution to the one involving just u and v, right? So, but I know that there can be no non-trivial solutions to the one just involving u and v, right? I know that there can never be any. The only solution is 0 and 0. And because of that, I know that this bit right here, this bit is garbage, right? This could never have happened, right? Let's see. So this could never happen.
Wait, why could it have never happened?
Because it leads to the idea that we started with some sort of non-trivial solution there, sort of forced this one to have a non-trivial solution. But we know that u and v started out by being linearly independent, right? Linearly independent. And what linear independence means is that the only solution is 0 and 0.
Oh, okay. So there would be no 2 and 3.
Could be no 2 and 3. There's no solutions to that. The only solutions to that can be is 0 and 0. Because if there was anything else, Carrie, then that would lead to something like this second pink highlighted thing. And we know that never happens.
So the question was, if u and v are linearly independent, then so are the vectors u plus v and u minus v. So that's just not true.
Right. So if I know that u and v are linearly independent, that forces u plus v and u minus v also to be linearly independent. Yes.
Wait, why? Because I thought the whole point was that we couldn't. Or you're just saying that the only solution would be the trivial solution to u plus v?
Right, which is exactly the same thing as saying that they have to be linearly independent. Yeah,
okay.
Totally. I'm going to say, I know that we're over time by a minute, so I apologize. I will say that I've got office hours this afternoon from 1 to 2. So definitely come by and check me out if you've got questions. I also have office hours tomorrow from 1 to 2. I will post this video to Moodle, and I will also record the other class, and I will post that too. So you're welcome to take a look at that and see if there are any other questions that popped up. Otherwise, shoot me an email if you've got any questions. Good luck in your studying. Get lots of sleep the night before. You will do great, but get lots of sleep. I'll see you guys,
Thank you.
see you guys later.